1, 2, 3, 4, 5. Hi, folks. Thanks for waiting. My team's up. Oh, not that team. Well, we got a few people watching. Thank you so much for joining me. To the 8 faithful in the chat. Just making sure my mic is working. I think it is now. That looks like the correct microphone. Yeah, that's working. 1, 2, 3, 4, 5. 1, 2. We're doing our second half of operating systems today. I'll be with you in a minute when I just switch my screen over. G'day folks, how are you going today? Thank you so much for joining me for the second half of our operating systems lecture. I'm just going to open my Teams and see where we're at. Where are we at? Where is my thing? Morning peeps, morning admin. So I have to tell you a story, which is that somehow, I don't know what I did, but somehow YouTube liked my last video on operating systems. And since Monday, that video has had 2,000 views, which is interesting. So if you're here because you've seen my first video on operating systems and you're hoping for a thrilling conclusion, I hope not to disappoint you too much. It will be a conclusion, but I can't promise thrilling. I can only promise some fun and a little bit of operating system excitement. Folks are telling me that's amazing in the chat, and I agree, it is amazing. I'm astounded and a bit confused because normally, like, you know, when people talk about algorithm hacking for YouTube, or they're really trying to get YouTube famous, the way to become YouTube famous is probably not to have 2-hour live to camera rambling lectures about operating systems with a bunch of live coding and assembly, which may or may not make sense. That's the general kind of rule of thumb in YouTube, is that if you want your video to be popular, don't have an hour of ARM assembly coding at the end of it and ill-advised jokes and one-liners. But there you go. I suppose there's an audience out there, and if you're here for the bad jokes and the ARM assembly programming, then welcome. I'm just going to recall what we did last time. The only admin time thing is to make sure you finish your assignment, which should be very clear to everybody, and to work on the quiz, which is open this week only. It's not that hard. It's got some exam questions. It's got some other things just to keep you thinking about the topics which we've covered and remind you about what we actually do in this course and what it might seem like when it was in an exam. Operating systems. We had a discussion on Monday about what an OS even is, what its roles and responsibilities might be, and we talked then about this concept of privileges for a process. So an operating system really doesn't make sense unless it has some way of keeping a different program in its box. So it has to have some kind of privilege system. So, you know, the operating system has a box. I don't know why I've gone with this box metaphor, but my YouTube fame has given me this serious hubris. And we want to put our application in there, and the OS lives outside the box, and the application can't escape, right? Or at least the OS can limit it. And this idea has sort of gone around and around. It's been back in more recent times with the idea of sandboxing. Sandboxing applications, which I've forgotten when that was invented, but it became very popular when people started to think about how programs work in an operating system like iOS or the mobile operating systems that Apple provide and Android, because they are an operating system. They have apps, but the apps get even less privileges than they would normally get on a regular desktop operating system. So they're even less able to mess up your computer. But there does need to be, with an OS, some way of keeping an application in a box, whether it's a sandbox or a bigger kind of box, maybe a shipping container, or a large enclosed stadium. It still has to have some limits, and the main limit is that, or the main reason for that is that the applications have, well, there are multiple of them on a computer these days, on a multi-computing or multitasking operating system. Lots of boxes, and we don't want our apps, we need to actually switch them in and out of a running execution state. So we take their context of execution and sort of put it on the shelf for a while and bring the other one out, bring the other box down and play with that one for a while, let that run for a while and put it back on the shelf, get the other, so we can share access to the shared resources. And we also have some way of preventing these apps from messing each other up. So if they've got their own bits of virtual memory, those are separate, and the operating system is in charge of that kind of stuff. And we talked last time about how, indeed, your microbit, well, my links don't work anymore. No, they don't work because I'm in whiteboard mode. Your microbit does support a very simple privilege model with two kinds of code, privileged code and unprivileged code. And more or less, the important thing is that the privileged code can control the memory protection unit and mark memory as being read-only or not readable by unprivileged code. So if you were going to write an operating system for your microbit, you would have to make use of these privilege levels. And we talked a little bit about that SVC call instruction, which reflects on the way that applications in our operating system context, I'm now really doubling down on the box metaphor. Applications need to be able to send a message to the OS to ask for something, because they're stuck in their box. They can't do anything without asking. So they need to have some way to talk to the OS. And the way that we do this in most operating systems is usually something called a system call, which will be a special function that an application can call, but it's a function which is actually owned by the operating system. So it gets the operating system to do something on the application's behalf. And often these system calls can have arguments, do all kinds of things. Like a classic system call would be the one that you use to print characters on the screen. The operating system is responsible for the screen, and it's responsible for moving characters between your program and the screen. So printf, or just regular print, is likely to involve a system call. Someone's asking, are there system calls in higher level languages like Java and Python? Absolutely. There are system calls in higher level languages. This is how operating systems and this is how application programming works. There's a lot of things that you run which are a system call. I can't speak too much for Java because I don't really understand how the Java VM works. Maybe one of these days I'll have to teach COMP2300 and then I'll have to find out. But I know for Python, like I guess you haven't done networks yet, but if you want to have a socket, if you want a network connection in Python, you import the socket library and then you say, make me a socket. And that runs in the background a system call to your operating system to get you a network socket to talk to other programs. There's another question here about Android Studio. Oh, you've got 2100 brains. Yeah, also forgotten how 2100 works. I did tutor 2100. I took 2100 in 2005. So I presume it's the same. It still uses Java, kinda. But it's in Android, so I guess you could be writing in Java, not Kotlin. Anyway, no, absolutely. System calls are a fact of life. Anytime you're doing system programming, which would be any kind of programming that requires interactions with the operating system, you will have to do system calls. They're usually wrapped up in some library provided by your programming language. So the example I could think of just off the top of my head was Python's socket library, which will run system calls to arrange network connections through sockets. Another example in Python, the threading library, if you want to do multi-threading in Python, that will run system calls to fork processes and run little separate threads. Yeah, someone was thinking that in a system call, we have to ask the OS for internet. Indeed, that would be, at some point, something is running a system call there to get your application connected to a network. Yeah, absolutely. Anything, the network system, that will be run by the operating system. A system call doesn't have to be like a difficult ask. It's just anything, right? Any connection to the computer, you're asking the operating system and the operating system does it for you. We're not asking for the world here, we're just asking for a URL to be fetched for us. System calls need to be done to do that. So that's the way that the application communicates to everything. The OS is in between, and then there's like literally everything else. Hardware, network, hardware includes like your screen. You want to put pixels on the screen, there's going to be a system call for that. Interaction with peripherals is a system call. Everything's a system call. I hope I'm not oversimplifying it here, but literally the stuff in device drivers, I guess I could be wrong, but in the vast majority of general normal interactions on a computer, you would be getting the operating system to communicate to device drivers to do stuff with a peripheral. Where was I? System call. Oh yeah, and we explored in assembly in ARM for your Cortex-M4, which has obviously a simple model, how a system call might work. And the way you do it is with a special instruction, which is only for doing system calls, the supervisor call instruction. Sometimes an operating system is called a supervisor for all of your apps, right? So the operating system is living out here and it's got all the apps on the shelf and it's supervising what they're doing. That's its role. And we learned about how the SVC instruction lets you have an argument to define what kind of a system call it should be. And we also learned that the only thing this instruction does is dump your execution state into the SVC handler. So obviously, if you're writing an operating system, the operating system would have to define the SVC handler to work out how to handle all of the system calls, and it would define a different kind of behavior for each argument, some kind of big switch statement going through all of the integers that it could get out of that immediate in the instruction. And we also did something fun, which was working out exactly how to get this data out of the instruction, which was involved a little bit of stack hacking, which seemed scary at first, but it wasn't too bad after all. There's another thing, deferred supervisor call. I don't know what that does. I know it's there. I didn't write this slide, I suppose, or maybe I did and I've forgotten about it, but I suppose it is what it says, a supervisor call which might be run later with different priority rules. Oh yeah, you can set the priority within the control space for PendSV handler, whereas the other one, SVC handler, maybe you can't change its priority. We did this. Oh, how do system calls work on Linux? I think that's a video, so if you want to know how they work on Linux, which is a good start in how they work on everywhere, go and watch that video. Okay, today's work, types of operating systems. I guess we think of operating systems as being mainly Windows or Ubuntu, whereas like the most important thing to have would be a start menu and a GUI and programs down the side. But I just want to say that overall, most operating systems don't run on a computer that a human runs. They probably run on computers that are running in some kind of embedded scenario. For instance, a car. So we'll just look at a few different types of operating systems that would have different requirements, or maybe a bit more esoteric. One idea is this distributed operating system concept where there would be lots of different CPUs, each with a small kernel, just to communicate between them. A bit of a more abstract concept, sort of a swarm approach to computing rather than a single CPU modality that we normally think of. And here's one which is quite important in embedded systems, the concept of real-time operating systems. So the idea of a real-time operating system is that it would be designed to work in an environment where you need to have a very strong guarantee that certain actions will occur by a certain time. It doesn't need to be fast, it just needs to be able to guarantee the time frame. And so you might need that in, for instance, controlling a car. If you're writing self-driving car software, you would hope that when you run the function to say steering wheel turn right now, it's not going to be suddenly deciding to do a context switch to another application and decide to index the spotlight, right? Or the find menu, right when you need to turn the steering wheel to the right. So you need to have some more guarantees about timing in a real-time operating system. There's this funky slide here. Fast context switches should be fast anyway. Small size. We expect everything to be small. Do we want RTOSs to have real-time response? Well, not quick, but predictable is the important thing. It's not that we're asking for very fast responses, but we need to know that this response will be no more than 2,000 microseconds or something. Multitasking, often, but sometimes that's required, but I guess if you have a computer to drive your car, it doesn't need to also run Microsoft Word. Should it be low level? This is usually needed to have some low-level programming interfaces. Should you have inter-process communication? I think that was a basic requirement for an operating system. High processor utilization, maybe. So RTOSs, we often think of them in two important fields, which would be robotics or cars. But they also, weirdly, are useful in music because if you're creating a kind of musical system, these guitars, this is a system I worked on, by the way, some years ago. These guitars each have a little single board computer attached to them, and they were part of they've been used for many things, but they were, in this instance, part of a kind of installation. They were sort of self-playing guitars. Introducing Microsoft Car. Now that would be good. So with music, as you found out with coding up byte beat on your microbit, if you don't continually update the next sample, then your music stops playing. So if you've got some waveform and you're trying to keep outputting the waveform, and you suddenly have some delay, context switches away to Microsoft Word, then you've suddenly got a bit of sound that isn't there, and that sounds really bad. So something about real-time music playback on a computer requires the operating system to give pretty good assurances of when it will be able to send the next sample or process the next sample. In a non-real-time operating system, generally we have to have a fairly large buffer for doing that. But in a real-time operating system, you can have smaller buffers because you have better guarantees. And the single board computers in these cases are, they're another ARM board called a BeagleBone Black. BeagleBone Black, which supports some particular kind of real-time extensions to Linux called Xenomai. And the folks who are working on this music computing system with that BeagleBone Black, they made a little board that goes on top of it, which gives you some very high performance inputs and outputs, so that you can do some cool sensor stuff with music at a very low latency, because you don't need to have huge buffers to cope with accidental context switches to Microsoft Word. Robots, obviously, if we're running a robot, we don't want it to stab anyone. This robot was being designed for doing an ultrasound. You can see it's got an ultrasound probe there. This is a sort of off-the-shelf robot arm from a group I used to work with, and some students were designing or experimenting with ways for it to be automatically using an ultrasound on a potential patient. Here's our patient here. The fake patient is a big bit of rubber, and there's the ultrasound machine. You obviously don't want that robot to accidentally sort of squish someone. It needs to be controlled in real time with very strong guarantees about timing, and the car thing. So yes, real-time operating systems, it's probably one of the ones you'll hear about, because they do show up in embedded applications where we more and more rely on computers to act autonomously, and we very much hope that they don't do anything bad. So we need to have results in a real-time operating system delivered just in time, and we need a guarantee about that, not just that the result will be correct, but that the time will be correct. So what and when are important. Predictability, not performance. That's the thing with RTOSs. What about embedded operating systems? These are more like the operating systems which would run on something like a microbit. So the microbit, I think we discussed on Monday, it doesn't have a virtual memory capacity. Virtual memory, it can't do that. It doesn't have hardware support for it. What it does have is memory protection. So you can have a simple operating system on it, but not Linux. So there are other operating systems which are simpler, maybe just designed to run one or two things and provide a few services for a little board that needs to connect to the internet every now and then and have some GPIO to interact with a kind of device. So an embedded operating system in general is any OS which is designed for a computer which is embedded into another thing. So I guess in the car case, that's also an embedded operating system. You often have, you'd have things like your fridge or your TV, or hopefully not your toaster, things that around your house that have little chips in them that are probably more powerful than you think. And sometimes they run little operating systems just so that there's a nice environment to program them, so that when the manufacturer is creating the one program that it has to run, they don't have to work on bare metal. They can work with an operating system and have some libraries and support to do things like connect to the internet, operate hardware, work with data, etc. Yeah, so these are often very small, don't really have user interaction, and they're the things which run on most of the devices in the world if they don't run a bare metal program. So the example here was of a coffee shop, and the question I guess you could ask is, are there any operating systems in this picture? I suppose there could be one in the coffee machine. I'm not really sure. That would probably be bare metal, but it could have a embedded OS in it. The coffee grinder, maybe, if it has like a timing system or some sort of coffee dosing capacity, it could have an OS in it as well. These grinders look like they're a bit basic, so maybe they're just a on-off kind of scenario. A few questions. How specialized do OSs need to be for their use cases? That's like asking how long is a piece of string. I think that there are it's unusual for operating systems to be particularly specified to use cases, I think. In general, folks have operating systems that are designed more like for the kind of computer that they work with. So there'll be operating systems that support Cortex-M4, Cortex-M3, these kind of microcontrollers. Operating systems that support something that does have a virtual memory unit, but it's a very light operating system. I'm thinking of something like Yocto Linux. That's like 65K or something. It's like a very, very small Linux implementation that would work on a CPU that we think of as a normal CPU, but it's going to be a very bad CPU, very slow and low power, and not have much memory. Some asking also, can you have an RTOS that facilitates music programs as well as robots? Well, I guess we tend not to have OSs that do support music in particular. So when the folks were doing that project, developing the board we were using, by the way, it's called this, Bella.io. It's a platform for beautiful interaction with sensors and sound. It's a shameless plug, but these are some friends of mine at Queen Mary University of London who are designing all kinds of different embedded interactions and allowing you to set this stuff up on this little board. It's a really cool system. They're a little bit expensive if you want to explore one. If you want to do a project in it, come do Laptop Ensemble and we might talk about Bella, and you can have a go on one of the ones I have. Bella uses a system called Xenomai, a real-time development software framework cooperating with the Linux kernel. So even in this instance, Xenomai is an extension to Linux. So we're taking an existing, everybody knows about it, a lot of eyes fixing it, operating system, Linux, and extending it rather than replacing it. And this Xenomai, I don't know where it's used. I presume it's used in a lot of different systems. I think that the system that Bella works with, which is that big old bone black, I think these folks were really aiming at robotics as the use case. Oh, see, there's a robot, a white robot. So they're thinking about robots. They're thinking about sort of experimental research, self-driving systems, different kinds of scenarios that would require or allow some cool real-time operating system. The thing that you get here, it's a normal ARM Cortex A8. The A series is like the big sibling of the M series. The M series is just much simpler. The A series gives you a lot more capacity to do normal computing. You can run Linux on it, etc. And this one is cool. This particular processor is cool because it's got these 2x PRUs. It's called a programmable real-time unit. So they're a microcontroller which lets you have some real-time guarantees that can interact with Xenomai. So when the folks are developing the software for Bella, they take Linux with Xenomai and then they're putting a specific program onto those PRUs. And by the way, I think they have to write that program in assembly because they want it to work exactly in a specific way. So it does need to involve a bit of assembly code to work correctly. Coffee blender could have I should have an OS in my mug, I know, surely. I'll get my operating system's mug next time. The coffee blender could have programs that make coffee in different ways, exactly. So it, well, your grinder might have a memory of different grind amounts. There's not much you can do with a grinder except turn it on and off for a certain amount of time. So I suppose it could be, or it could be have a built-in scale, so it's measuring out a certain number of grams of coffee for dosage. Let's continue with the lecture. I've talked too much about embedded operating systems, but it's fun to think. It's fun to think that really when we think of operating system, don't think of Windows, don't think of Linux. Think of like your car's radio, and think of your fridge, think of your coffee grinder. There's a lot of computers in the world that require operating systems that have different requirements and they don't have a user interface. And someone does said that the microbit has user interaction. Indeed it does, but the chip that is built into the microbit is used in a lot of different things, the NRF52833. One particular thing it's used in, I think, is the Samsung Smart Tag. Yeah. That has the same chip in it that the microbit has in it, and there's no user interaction in that. It just exists in the world. This is an important topic, processes and scheduling. Trust the process. So this is a screenshot I took from my computer some time ago now, looking at all of the different processes that are running on my regular, I think this was a screenshot in Mac OS. And I guess my question would be to you is how many processes are running on your computer right now? How many processes are running on your machine? Well, there's my computer. How am I going to find out? Top? I never know how to run top. 542 tasks. That doesn't seem too bad. 543. We can have a little bit of a thought about some of these things. I've got 543 processes total running in my Linux Ubuntu OS right now. I've got 3 that are actually running, 2 or 3 actually running, and all of the rest of them are asleep, doing nothing. So, and then there's some other numbers here, 0 stopped, 0 zombie. Well, that's exciting, isn't it? Zombie processes, it's like the zombie apocalypse. Then I've got some stuff about memory that's being used. And each of these processes has a bunch of stuff about it. It's got a process ID. It's got a user that owns it. It's got a I don't know what that means. Priority, maybe? It's got a I don't know what that is. I should probably have done some research before going into this bit of the lecture. I don't know how to read top. It's got its amount of, I think it's amount of virtual memory, amount of reserved memory. 350 processors on Windows 10. That seems good. I think that when I took that particular slide picture, like I had tons. I don't know why I had so many. Oh, you can't see it. I'll just get the image in a new tab so we can see the entire image. Oh no, about the same, 522. 2 running, 2 stuck. Stuck seems bad. 588 18 sleeping. That's a different version of top on Mac OS, so it looks similar but not exactly the same. Ooh, and then I've got this other one, 2,247 threads. So even though I've got a lot of this number of processes, I've got a lot more things called threads. So I guess that suggests that one process can have multiple threads doing different stuff. So that's sort of like a sub-process, isn't it? Chrome using 3 GB of RAM. How much is Chrome using on my computer? Where's Chrome? Oh, it's gone. Resident. I think that's memory is actually being used. OBS is using 1.2 gigabytes. Firefox is using 1 gigabyte. And I don't know, Chrome's not using that much. Get some more RAM. That's the only answer. So typical normal desktop operating systems we use tends to have lots and lots of processes running all the time. So let's just define this concept of a process. Basically, it's a running program on your operating system. This is going to have the code somewhere, instructions for your program, current state, which we talked about state when we were talking about context switching, which would include your registers, memory, the stack, which is your regular stack, and heap, which is going to be separate memory that the operating system allocates for that program to use. It will have some knowledge of permissions or privileges. It might have the operating system might have its own model of permissions outside of that provided by the hardware, so building on top of that model to make it more complicated. And maybe some other open resources like files that are open for writing onto a hard drive, network connections, address space mappings, other kinds of stuff. So when we get all of these bits of information together, we can fully define the state of that process. So it's defines the process. Bad writing. Another Jurassic Park meme. Processes as far as the eye can see, all the way into the distance. There's processes all over your operating system, all happening at the same time. Who's that guy? So the exact way that a process is defined actually depends on the OS. It's not a completely decided thing. Of course, there are lots of similarities between definitions, but different operating systems have different ideas about how to do this. So what we'll talk about now is how we manage processes. Now, one way we could do this is that if we had lots of CPUs, we could just give a different process exactly one CPU to work on it. So each task has exactly one CPU and they talk together. So for instance, in this case, we've got 6 CPUs and 2 address, or maybe many address spaces, 3 CPUs per address space, and each of these processes has their own stack, their own code, and then I guess or their own heap, which would be part of the shared memory that's divided up into 3 bits. And no one ever has to move anywhere because everyone's got their own CPU. So that would be fine if we had lots and lots of CPUs, but we tend to have fewer CPUs and more processors. I guess in my computer I've got, I think it's an 8-core system. Sorry, I don't know. The 8 CPU system, but I have 500 processors. So there must be something else going on. I guess you could also have one CPU for all of your control flows. That seems like more what we need in our situation. There's our one CPU down there. And then there would be the address space, different address spaces, and a bunch of processors have their own stacks and code, and the CPU knows about them all. And then there would have to be some scheduler, which is defining which process should be running on the CPU at any one time. There was a good question in the chat there. I'll just get to that in a second. So yeah, in this scenario, we have to have support for memory protection so that these processes can't just invade these processes' space. We need to have process management so that we can figure out which program, each of these is an app, right? A1, A2, app 3, app 4, etc. Which one of these is working on the CPU at one time, because the CPU can only run one instruction at a time. It can only do someone's work at one time. And we'll have to have some way to coordinate shared memory. Symmetric multiprocessing. Now is where things get to be like a little bit more complicated, but also a little bit more like what we actually do. Because now, as I said, my computer here has 6 CPUs, 8 CPUs, sorry, that all share the same physical address space, and they can all run a different task at once. So we could potentially have 8 tasks running in parallel. Do I have anything else there? No. So there would have to be some way to then define, well, which things are running on which CPU. That one's working over there. And I can't do my things. This one's going over that one. And we still have lots of lots more tasks than we have CPUs, but we can run many of them in parallel. But maybe some of these tasks would like to use multiple CPUs because they're doing something complicated, which is what we can speak of in a minute. Processors versus threads. So I mentioned before that we have 500 processors, but then like 1 million threads. So what's going on there? In general, a thread it's often defined to be a kind of lesser thing. So a process can have many threads. That has its own threads. And the process is usually responsible for defining or starting up, stopping, and managing those threads by itself. So the process would have their own registers, stack, resources, etc. And then the threads will have their own registers and stack, but share other process resources. And then one process can create and manage many threads. An example of what you might do is if you've got a task which is repetitive, like processing, taking a line of pixels. This is a line of pixels in an image, and you wanted to make those pixels pretty. This is a really bad example, but you might have some small program that takes one pixel and changes it from being boring to pretty. That's my small program. Or just a function that does it. So you might, and you can do this in Python, get your threads library, which would ask the operating system, hey OS, I'm going to make some threads now. Can you help me with that? I would like to have 4 threads which are going to run this function. And when they're done, can you please take run them again with another pixel from this pile of work to do, and keep doing that until all the work is done. And the operating system says, okay, I'll make your 4 threads, and then your threads just start eating away at this work, and the operating system is responsible for making sure that the threads go on the CPUs that are available. So if we have multiple CPUs, which all of your systems do, no one has true single CPU systems anymore with just one CPU, except for something like a microbit. All of your desktop and laptops and phones and watches probably have multiple CPU systems. So multiple threads can run simultaneously on different CPUs doing different work. So this stuff, just to mention here that this stuff is all defined by people, and there are arguments about what is the best way to talk about them. And there's a thread here from Linus Torvalds, who designed the Linux kernel, against threads, Torvalds versus threads. He says, someone else wrote, we need to keep a clear concept of threads. Too many people seem to confuse threads with processors. And Linus Torvalds says, in his very classic blunt style, no, there is no reason to think that threads and processors are separate entities. That's how it's traditionally done, but I personally think it's a major mistake to think that way. The only reason to think that way is historical baggage. So, okay, I'm just going to walk away from that. That got heated quickly, didn't it? Walk away from that argument. But people do still talk about processors and threads, so obviously, getting to be 25 years on from that email, the concept has stuck around. But just to mention that we do have multiple multiple ways of defining this stuff. It may change in future as we as a society invent better ways to define computers. I'm going to talk about a few questions that have shown up in a second because they're interesting. Someone just said, building a PC only requires installing a single CPU chip. Does that chip itself contain multiple CPUs? And the answer is yes. What's the chip in my PC? AMD Ryzen 7 3600 something? I'm making it up. 3700? I've forgotten. 3700X. Die. Let's have a look at the actual thing. Not die. I want to see what's actually on the chip. I'm not going to get any good pictures of it. Well, here's a 6-core one. Come on. Oh, I am human. Come on, buses. I can't do a capture the bus. The more buses. I can't think about captures while I'm trying to do a lecture. Okay, here's a photo of a CPU, and this one actually apparently has 6 CPUs. Really? It looks like it either has 4 or 8, but you can see that there's huge amounts of stuff, all this complicated stuff which makes up a CPU, duplicated multiple times. This is a picture of what the CPU actually looks like inside the case, cutting away all of the stuff protecting it. The actual silicon die will have multiple CPUs replicated and positioned all together so that they can all access the same memory. That's a Ryzen 5 3600, which I thought was a 8-core chip. Yeah, no, it's a 6-core chip. I don't know how to see 6 things here, but apparently it's so. Anyway, maybe it's an 8-core chip where 2 of them don't work. Sometimes that's what CPU manufacturers do. They make a lot of these dies, and they don't. Not all of the silicon dies that they create are successful. So sometimes they take ones where it's mostly working. Maybe they've got like a 30% chance that 2 of the 8 cores don't work, or don't work very well. So they just take that die, turn off those ones, and sell it as a 6-core chip for cheaper. Classic. They call that binning. So they don't put everything in the bin, but they find the dies and test them and then put them into different categories depending on how good they are. So when you buy, for instance, an AMD chip, the very expensive ones are the smaller number of dies that happen to be working really, really well, and they can be clocked fast and have all of their systems working on the chip. Yeah, so you can see this is a typical chip. This is now a little bit old, Ryzen 5. Number of CPU cores, 6. So there is no chip that you can buy for a computer that you would build that would only have 1 CPU core. That was like many years ago that they stopped doing that. The last ones were like the Pentium 4s, single chip that came out when I was in high school. Since then, the 2-core chips became popular, and then 4-core chips became popular, and it sort of stuck around 2 and 4 for quite a while, and now people have started to find better ways to use many more cores, so they're going for more. And then if you buy the really expensive ones like Threadripper, that's a very expensive CPU. I want it to tell me what it is, but what is it? No, specs. Architecture? No. It's not going to tell me what this chip actually does. Anyway, there are AMD Threadrippers that have like 30 cores in it. How do they get these things so small? I don't know. I'm not an engineer. Well, actually, I think that sometimes the individual transistors stay the same size, and the things like the Threadripper are just getting to be like physically bigger, right? So the die on your Ryzen might be that big, but the Threadripper might be that big, so they can physically fit in more of those cores. And I think that at some point, we get to have these chips now which have a lot of cores, like 16 or 32. It's starting to get a bit crazy. And the reason it's starting to get a bit crazy is because you have limitations about that many cores accessing the same memory. Like the memory, you still have the same bunch of memory for all of those cores together. What's called a unified memory architecture. And as those cores have to access memory, well, your litter operation on your microbit, you can be sure that no one else is doing a litter because there's only one CPU, right? It's only you. If you've got 2 cores, the litter, if you're trying to litter and another CPU is trying to litter, the second one's going to have to wait. And if you have 4 cores, you might have a queue of up to 4 people waiting to load from memory. So usually if you've got a couple of cores, maybe you know, it doesn't happen all that often that there's a clash, that someone has to wait. But if you've got 24 or 32 cores, suddenly your chances of having to load memory at the same time become much higher. So things start to become bad. Up to 64 cores, right? Yeah, things start to become bad. Thanks, folks, for Googling on my behalf. Yeah, the current AMD Threadripper architecture can have up to 64 cores. Each of those cores can support up to 2 threads using a system called hyperthreading, which we'll discuss next week. And then for the Threadripper, I think it starts to have non-unified memory architecture, if I'm right. Threadripper, I'll just ask on the chat. You guys can has NUMA, non-unified memory architecture, right? Yeah, I believe it needs to have a non-unified memory architecture to cut down the chances of so many cores clashing on memory. So you need to have separate chunks of memory that are disconnected from each other, with each core addressing just one of those chunks, which then becomes an issue if you've got a program on core A and another program running on core 1 and core 56. They have no way of sharing memory. So then you have to have some other way of specially making a tunnel through the shared memory, through the non-unified memory. Anyway, it gets complicated. It's very interesting, but probably not the topic of the day. I do want to talk about processes before we end. Process control blocks. So every process will have this bunch of information, an ID, a state, is it a zombie process or a running process or a sleeping process, some things about scheduling attribute, maybe if it needs to be run in a minute or it can sleep for a while, the CPU state, so that's the regular context, memory attributes and privileges, other resources, files, etc. And we can put all this stuff together into a kind of data structure for organizing our processes. So each process will get a different block, 1, 2, 3, different processes. So then the operating system can keep track of all those processes and decide who should get to go next. So it's like a data structure for processes. So here's some process states. A process can be created. It's ready to run, but not yet considered by a scheduler. It's ready to run, waiting for a vCPU. Running, holding a CPU and executing. Blocked, so that might mean that the process is waiting for a resource. It might be waiting for you know, the network sender to have sent the last bit so it can then run and send the next bit. As you were doing in your labs this week, you had to block your thread of execution until you knew that the serial sending routine had completed running. It might be suspended, it might be swapped out of main memory and waiting for some more space, or it's just not needed for now, it's waiting for someone to switch back to that window and start to use it again. So here's a little diagram of what this process could look like. So you have we should do a digital pet version of this. The process is born, it's created, it's moved into main memory from like a SSD or something, or some other cache. It could be dispatched and then it's running by a scheduler. It could find that it's blocked by requiring some resource which is being used, so it's sitting in this blocked pile. Then it could be released and ready again, and then dispatched and running again. It might run for a while and then time out. The OS is like, you've had enough time, I'm going to put you back on the shelf for a second. Then it runs again, then it's blocked again, then it is blocked for so long that the OS says, look, you've had too much time in memory, I'm going to suspend you for a minute, put you back into some other lower level memory which is slower and further away, or it could be on disk in swap, although we tend not to do that these days. We're blocked and suspended, but now we're released, so we're ready and suspended, and then we have to be reloaded back into memory. This is the story of a process's life. Run for a little bit more, just get suspended while we're running for some reason, reload, run, and then we say, finally we're done, and tell the OS we're done, and we get terminated and die and turn into a little angel process flying through the sky. By the way, my Tamagotchi died at the end of last week, and I'm not resurrecting it anymore. They're too painful to organize. And it sat on this kind of like twinkle, twinkle, little star angel flying through the sky. Whoever makes the OS for the pet is the greatest of all time. It could be you. First come, first served scheduling. So I've got a few slides to illustrate what could happen when we're actually scheduling a process and what the strategies could be. So one strategy, seems like a good one, would be first come, first serve. So I've got here 3 different tasks. Task 1, task 3, task 1, task 2, task 3, red, blue, and green, and that are arriving on the CPU, and they need to be run. And you can see this one down here, the red task, wants to run for a little bit of time regularly. So it keeps running regularly for that little bit of time. The blue task has a bit longer, but it wants to run once and then again, and then once and then again. So sort of intermittent task. And the green task is also running regularly, but it requires a longer amount of processing. So if we do first come, first serve, the green ones come in first. So it's going to get scheduled first. It's going to run on our one CPU in this very simple system. Now one CPU, it runs here. Then the next one in the queue is the blue one. So it's running next, but only its first one. When that completes, we go to the red one. Okay, and then the next blue one, and then the next red one. Then we've got these 2 other red ones by this time have been queued up, so they run too. In that intervening time, a green one has shown up, so that runs, etc., etc., etc. Now, I'm not going to do the maths in front of you, but from this diagram, you can see that the waiting time for a task ranges between 0 units. I guess we could call this seconds, but it's a fake CPU, right? It's a very slow CPU that has to wait for seconds and seconds before things are scheduled. The waiting time is between 0 and 11, and the average waiting time is 5.9. The turnaround time, which is the time between a process waiting and it completing, is between 3 and 12, and the average is 8.4. So far, so good. So even in this deterministic, very boring scheduling schema, you can have different outcomes depending on which thing comes in first. So here's another one where instead of, instead of selecting the green one, we select the blue one first. So the blue one ends up coming in first, then the green one, then the red one, then this other blue one, then the other red ones. So this one is just sort of reading from the bottom of the, reading from the bottom rather than the top for deciding which order things have arrived. So in this one, the average waiting time is now a bit lower, 5.4, and the turnaround time is a bit lower too. So we're not sure which one of these would be best, starting from the top or starting from the bottom. There's no real way to know that. We do know that overall, first come, first serves gives the shortest possible maximal turnaround time. So the upper bound on your thing completing, your process completing, is lowest under this scheme. Let's look at another scheme. Another classic one is round robin scheduling. So in this way, we define a kind of a longest possible time for things to wait if there's other stuff waiting. So the green gets a go this time, but only gets a go for one time unit, and then we switch into blue for a little bit. Then we switch into red. So now we're sort of going green, blue, red, red. The red's now finished. Well, that's one complete red, that's another complete red. We're still waiting for those blues and greens to finish, and they're not going to finish for some time. Well, that blue finished there. We're still on the first green. 1, 2, 3, 5, 6, 7, 8, 9. 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. It doesn't finish until up here. So that's the turnaround time for that task is now much longer because it's, even though it's been running regularly, it's being stretched out. So this scheduling system is good if your task is very short, but if your task turns out to be long, it gets stretched out over time and might take a longer time to run. So the good thing here is that your waiting time for your task to start is going to have an upper bound. But your turnaround time might be much longer. It can be up to 20. The average here is lower because the short tasks get to run quickly and finish. So that brings down the average turnaround time by a lot. And the average waiting time is small as well. So you can think about this. When might you want to use FCFS? What about round robin? And so another final Jurassic Park meme for today. This is what the operating system is doing when we've got processors. We've got 3 angry dinosaurs that are each process, app1, and they all want to use your CPU, all of your CPU's resources. And it's the operating system's responsibility to make sure that each of them gets picked at a reasonable frequency so that they have a low waiting time but also a low turnaround time. And then in week 12, you actually get to have a go at building an OS, which is pretty fun. I've got a question slide, but I'm just going to point out a few things for you to read, because operating systems are fun and interesting. I should just give you this as a lab, how to make an operating system. We'll look at that in a second. There is a way to run Linux on an 8-bit, really bad microcontroller, one that's even much, much worse than what you have in the microbit. But it involved some hacking to kind of have fake virtual memory. And it was very, very slow. Kernel writing 101 is pretty interesting on just getting started writing a kernel. And for this topic, I really recommend you look at this book, which is available through the ANU website. If you're interested in Unix, have a look at the $7 History of Unix. How to make a computer operating system. Okay, we should take some basic computer science courses. So you're doing that, that's pretty good. And then we should learn a high-level programming language. Well, you've done that already because you've done COMP2300 and 1110, so you know Java and Haskell. Then you should learn an assembly language. So I think you've done that as well. You've learned ARM assembly this semester. So I think you're getting it together. Now, complete an operating system tutorial. So I guess you'll have to have a look at that. But what they're suggesting you do here is actually look at how in depth some other operating systems work. So a good one that a lot of people do is one called Linux from Scratch, which is an online book where you assemble all of the parts that go together to make Linux work on a computer by yourself. It's generally not something you do on your main computer. You usually do this in a virtual machine just to see how it works. But it's a very interesting concept. So it's not a distribution, because you don't get anything from Linux from Scratch. It's a book telling you how to go find the Linux kernel, how to go find the tools you need, how to find bin utils, and how to find a shell and get this all together into an operating system that a user could use. Then you have to figure out your goals of your operating system. So do you need memory management, security, apps, GUI, user interface? Very important to know the goals of your OS. And then just go and build it, right? And then what do you do? Oh, set up your version control system. After you've built it, you're supposed to do that. That doesn't make sense. Then you should decide on a bootloader. That's important. Choose a kernel design. Start small. Good idea. And test it on a virtual machine. So this is not a bad WikiHow. I suppose it's a bit, the effort's a bit jumbled up. You're supposed to network with other operating system developers. You could look at r/r/osdev on Reddit, which is fun. Probably that's the first thing I'd do. If I was interested in operating system, I would look on osdev on Reddit to start with, rather than wait till the end. Okay, well that's enough silliness on WikiHow. Don't do any of those things. Don't do any of those things right now. I think that there's folks in the labs. But I'm going to show you one little wild thing. On did I have my? I'm going to put this somewhere else. This was my demo from last week. My example from last time. Oh, there are questions. You can run Linux on a microbit. You can't run Linux natively. I think they had some hack to get virtual memory to work virtually. which was very slow and bad. You wouldn't want to do that, and probably not actually working. It was a perverse example. Just going to put this back in my examples. That was week 10. No, week 10 interaction demo. Look at that another time. Now, for this week, what I wanted to do was something that you're going to see in your labs next week, just a little bit of a demo, just for 5 minutes, but I'm going to take a wild call, and I'm going to change the name of this main file from main.s to main.c. And I'm going to delete everything in it. Because now, folks, just for week 11, just as a special treat, we're going to use a different programming language. We're going to use the C programming language, which is a little bit weird. And you might be thinking, that's impossible, Charles. There's no way that this would work. How can I just start writing C in my on my microbit? But actually, everything is organized for it to work. So int A equals 6, int B equals 37. Let's just do return A plus B. So I hope this works anyway. Is my microbit plugged in? Here we go. Whoops. Yeah, it works. Everything's fine. So here's a C program. The C programming language is very important in the history of operating systems because it was developed around it was the programming language used to create Unix, and it's very deeply entwined with the development of portable operating systems that would run on different types of computers. So it's fully entwined with that history. Before that, you would have operating systems just for a specific type of computer by one manufacturer, one, in fact, computer that would have special ISAs, special instruction sets. It would be a lot of assembly written to get them to work. And then the innovation was to have a language which was a little bit above assembly, which is C, that would work across lots of different types of computers. And you could have different requirements per system. So I'm going to build and debug this, and I'm actually going to just prove to you that it is compiled by doing view disassembly of main. Now I don't know why doesn't want to give me the split window automatically. I don't know what happened there. So where's my 6? Int A equals 6. This is so far a lot like what we were doing with the Godbolt website some weeks ago, but now I'm running the C code on my microbit. And as I got into the start of the function, it immediately kicks me over into the disassembly, so I can go down line by line through the assembly. So that's putting 6 into R3 and then storing on the stack. As usual, we know that the unoptimized GCC compiler wants to make a lot of space on the stack for every local variable. Puts in 37 on the stack. Then the next thing it has to do is add 6 and 37, so it loads them back off the stack. It probably didn't have to do that, but the compiler has been put into the least optimized mode. And then it's going to add R3 and R2 together, and then move the result into R0, which is our the register we're using as return value. Deleting some things off the frame, and then moving that back to the stack pointer, and then returning. And then we end up in program end. So a perfectly valid program in C. So what can you do in C? Well, in the way that we've set up your template, you actually can't do a lot, because normally when people learn about a programming language, they learn about that programming language and what's often called the standard library of functions that would come with it. And in this course, in 2300, we specifically don't give you any standard library of functions. So you can write in the C programming language, but if you want a function in C, you have to make it. So you can't do printf, print things to the screen. The microbit doesn't have a screen. There's nothing for it. It doesn't know about how to do that. So none of those functions that you would typically learn about in a first go at C are going to work. There's no hello world. There's not going to be anything that works in the way that you would expect. How come it didn't crash when we told it to load C? Well, you could have been doing this all the time, but just when you run build or run upload or anything, build your program, it runs this make file, and I don't want to spoil it for you, but it actually runs the C compiler to do it. So the C compiler here is the ARM version, ARM none EAB GCC, which runs first. I think all, oh yeah, so we've got to get the, make files are funny. They're like, I need the .o files, so you're going to take everything that's a .c file and a .s file and use the C compiler with it. So if you use a .s file, the C compiler is like, cool, that's an assembly file, I'll assemble it for you. And if you use a .c file, the C compiler says, cool, it's a C file, I'll compile it for you. And then it combines those with the linker and eventually uploads it to our microbit. So we did talk about this in, I think it was week 6, talking about the tool chain. So that's the tool chain that we do. So a few things about C that we might need to know. When you make an int, that's a 32-bit number. And if you make an, I suppose, a char, that is an 8-bit number. So we'll see what happens, see how much stack space it dedicates for that char. It might be slightly difficult to work this out actually, but we can do it. What was I put into it? 6. So I think it's actually putting this, there's one thing is going into 12, one thing's going into 8 from R7, which is our frame pointer. That's the way that the C compiler set it up. So there's 4 bytes in between those two values, the two ints, but then this char, or character, an 8-bit value only gets 1 byte because it's one single byte on the stack. And the thing you can do with a char, they're called a char because they can contain one ASCII character, which you can put in that way. I'll put an X because I remember the ASCII value for it. Oh, what? This feels like it hasn't compiled. Oh well, I can't seem to get it to work. It's definitely not 6. I thought X was 120 in decimal. Something interesting that you can do with C, which is kind of the point of it as a language really, or one of the points of it, is it gives you very deep control over memory. And I'm just going to make this one point before I go, because you'll have to look at this again in your lab next week. It gives you deep control over memory. So as you know, in assembly, we often would store a memory address in a register. And so you would have to manipulate a memory address, get that memory address, get the memory at that address, and get it back. So we can also get a memory address in C. And the way we do that is by using an operator called the reference operator, which is this one, ampersand A. So that's going to give me the memory location of A. And the memory location of A is going to be a 32-bit number, so I can just put it into an int. I'll put it in D. And my makefile is actually going to break if I don't use every, it's going to complain about compiling if I don't use every number. So I'm going to take that value D, set it to be the reference to integer A and see what I get. Oh, it tells me that I'm not allowed to do it. Initialization from int star makes integer from a queen without a cast. Oh, I wanted to do it the wrong way, so I can tell you. But it's going to be you have to change the type of the value. So D is going to be the type int star, which means it's got the type, that's got the type integer, and D has got the type a pointer to an integer. That should work. No, it still doesn't work. Oh, you can't add them up. Come on. I was going to turn errors off. Let me add them up. Let me be unsafe. C. The whole point of C is to be unsafe. Where's my makefile? Error. No error. Safety is for fools. We were learning in assembly. We've been unsafe all along. Don't tell me at this late stage that we're allowed to just, I'll put it in there, that we aren't allowed to be unsafe. Not the makefile, I want the letter B. That's getting back that X. Anyway, we will, I've told you a little bit about C, and I've told you that it works on your microbit. You can write in C. It is possible. You're not allowed to do it in your assignment, but it's possible, and you're going to do some experiments with C and your microbit next week. You won't get very far because for C you really need to have all those libraries present, but we are at least can have fun with memory. The weird thing coding in C on the microbit is how limited it feels compared to assembly, because we all got used to writing in assembly and having full control over everything. And C, people often say that about C, it gives you full control, but it just seems like it's not quite touching the hardware as you're used to with assembly. So I'll stop there. I will say goodbye now because we've got to the end of time. And I will catch you folks on Monday for our last topic, which is architectures. We'll talk a bit more about multiple cores that week, so these topics are related. Folks, have a great weekend. Enjoy the rest of the labs this week if you're still in doing your work, and I will see you folks on Monday.